Explain gun recoil in terms of conservation of momentum. So I'm going to try to draw a picture of a gun here. Some kind of gun. I'm going to say this is like some long barrel of the gun. Here's like a little opening to it, right? And then, I don't know, I'm going to have like a stock on it. I'm not sure how to draw all the rest of the details. And we'll have a little part here. Has a trigger. I don't know. There should probably be something up here, right? I don't know exactly how to draw that part. Depends on how old and what kind of gun, I guess, right? Anyway, I'm not going to go back to wheel locks or match locks, are we? But we want to explain in terms of momentum, like, 'cause what is recoil, right? If you shoot the gun and you're holding it, it pushes back on you. That's the basic phenomena of recoil. But can we explain that in terms of momentum, right? So let me actually make a copy of this gun that I just drew, because I'd like to consider maybe like a final and initial type of scenario. So I'm going to draw, maybe here's like I'm just going to put the gun down here for a final type of scenario. And then let me go in here and I'm just going to put, like, imagine we got x-ray vision, right? And we can see the bullet here initially at rest. I don't know if that's where it would actually be, but whatever. There's a bullet that is in the gun. And I don't know if that's a good enough drawing, but I will try to copy that bullet now and see if I can drag it somewhere out front of the gun for my final picture. So again, this is initial, right? The initial picture has an initial momentum that is equal to 0 because the gun and the bullet are just sitting there at rest. But the final picture, therefore, must also have a momentum is equal to 0 if I can model this as a closed system. Well, which would be great if this were a sort of self-shooting gun somewhere out in outer space. But, you know, we'd like to, as we mentioned earlier, not limit our application of conservation of momentum to systems that have to be that isolated. But maybe if I think about this like representing the brief moment right when the bullet is fired, because it really goes pretty fast, right? So this would only be like a brief second after I pulled the trigger. And maybe I've exaggerated how much this gun has moved backwards. But the way I'm going to model this to explain why the final momentum might also be sensibly equal to 0 here is if I say, okay, the bullet is traveling really fast, right? So let's draw an arrow there and give it a big velocity v. But the bullet is a little tiny thing with a tiny little mass m. And we're going to say that the gun, in turn, has a much larger mass. Now, guns aren't necessarily that massive, right? But relative to the bullet, it's quite a bit larger. So I'm drawing a capital M for that. And we're going to explain recoil based on the idea that the gun is actually pushed back to have a small velocity in the opposite direction of the bullet. And so, in that sense, the final momentum, maybe I'll look at this as like the x component of the final momentum, would be in a standard coordinate system, right? I think you'd say minus little m big V for the bullet plus big M little v for the gun is equal to 0. And this could make sense, right? Basically what we're saying, though, is, I mean, this implies that the mass of the gun times the recoil velocity it gets is equal to the small mass of the bullet times the really large velocity that the bullet has. But they have, in that sense, equal amounts of momentum, right? Which is kind of amazing. So when I shoot a gun, it really crashes into me with an equal amount of momentum as it just put into the bullet. You might almost say, like, wait, really? But if they carry equal amounts of momentum, why is the bullet much more deadly if it like hits a living target, right? And I think the thing to recognize there is that the stock of the gun is designed to kind of distribute the force that as you decelerate the gun. So like kind of the way I look at this is like the gun is shot, it is now going back, you know, in a really brief instant of time. It acquires this velocity v, and now it's like my job as the gun holder is I have to stop it. I have to decelerate it. Well, otherwise it would go through my body, right? So I kind of have no choice. But the stock helps me do that because it kind of distributes the force that the gun applies to me and that I, as a Newton's third law kind of interaction, have to apply back to it to bring it to rest. It distributes that over a larger area, which makes it not deadly to me, right? Whereas, like, if you think about the area that the force of the bullet is going to be applied to, bullets are small and sometimes kind of pointy, right? So that's going to be a really small area, and therefore, I mean, it turns out later in this semester we'll talk a little bit about pressure. It's a much larger pressure, you could say, enough to potentially pierce something and possibly not be good for living tissue, but nevertheless they do have the same amounts of momentum, which I think is kind of a cool and mind-blowing concept. Let's check this against the answer here. So it says, considering the gun and bullet as a combined system that is isolated, when the gun is fired, the bullet gains momentum. So the gun must gain oppositely directed momentum. And that it doesn't say that there, but it's the same as we saw, right? Same amount of momentum. In reality, the momentum gained by the gun is experienced as recoil by the user.